Today we're going to talk about airfoil design. We've already talked a bit about airfoils, and we're not going to get into too much detail about airfoil design, so this will be pretty quick. Just wanted to give you a few pointers to help you with some of the homeworks. Okay, so first, let's just talk generally about airfoil shape. Why does it look the way it does? So some of these things we've talked about already. Here's, for example, an airfoil-like shape. We'll notice, at least this is for subsonic cases, right? It's got a rounded leading edge and a sharp trailing edge. Why does it have the rounded leading edge? It's actually doesn't have to, right? We could have an airfoil that was really thin, basically a sharp leading edge, sharp trailing edge. And in fact, in some ways that would be ideal, right? Because the extra bluntness is going to basically divert the flow more, potentially add more pressure drag, a little more skin friction drag because of the wetted area. Why not make one that's really thin? And that would actually be really ideal if, say, for example, the flow is coming just right. Then I can get a really thin shape. I don't have to divert the flow too much. I'm going to have a smaller wake, and that's going to have a really nice aerodynamic shape with low drag. However, the problem with this kind of a shape and why we don't generally have such thin sections is that they're not very robust, right? So if now the wind is coming, let's say from this direction, the free stream, I've got to navigate around this really sharp edge. That's a very steep pressure gradient that I've got to come against. And the flow is very likely to separate. Oops. So for example, that streamline up there is probably not going to happen. And instead it's going to come around and it's just going to separate, and I'm going to get a big wake, tons of drag right off of this airfoil. Now, if I could dynamically move my wing like, say, a bird does, so I can move this to respond to the inflow, and so that would be quite ideal. And that's actually why birds' wings, one of the reasons why the birds' wings are going to be so thin, because they are able to maneuver so quickly and adapt. But in general, for these large airplanes where we have a lot of inertia, it's just not practical from an energy standpoint. So we need a blunt shape like this. So as the airflow comes from different directions, the pressure gradient is not too severe, right? So let's draw the airfoil again. And now let's say I come from the steeper angle. There's a more gradual pressure gradient that I need to come around, and so I can keep the flow attached up to higher angles of attack. So if you were to compare these two, again, for a fixed design, then the sharp one may stall really quickly, whereas the blunt one, I can get up to a higher angle of attack before the pressure gradient is too adverse to navigate. Okay, so that's why we want a round leading edge generally. Well, what about the streamline trailing edge? Well, that one is maybe more obvious, but a bit surprising for how important it can be. Now, this is not exactly to scale because I'm freehanding it, but this is about the right perspective. That for, say, a large Reynolds number, an airfoil, it's a bit thin, let me redraw that. So an airfoil like this and a cylinder like this, they have the same amount of drag. Again, that's not exactly to scale, but it's not too far off either. Now the draw so we can actually see it. Say like this, right? About the same drag. Even though the cylinder is much smaller, and the reason why is that this is going to separate. It's going to create this big wake, a lot of drag, whereas the airfoil, as long as I get a nice streamlined shape, I can have hopefully very little separation, maybe a little bit at the trailing edge. So very small wake, low pressure drag. I of course have much more skin friction drag on the airfoil because I've got much more wetted area. But depending on my Reynolds number, especially for a higher Reynolds number, that's going to be a small, not as big of a contribution as this increase in pressure drag. So even though these shapes look quite different, they may have, quite similar drag. And this is why you'll see in performance racing or cyclists, right? You'll see all sorts of streamlining, even spokes on a wheel, right, will be streamlined because of this excessive drag that can be created. Okay, so what kind of shape do we want? Well, that's just kind of the broad terms. We're not going to get too much into the details of the shape. That's really an optimization problem. But some things we want to look for as you're comparing different airfoils. We want to look at the lift curve. So let's say we look at the lift curve. It's angle of attack versus CL. If I had one airfoil that looked like this and another one that looked very similar, but looked like that, well, all else being equal, the blue airfoil is a superior one, right? Because I can get to higher angles of attack before the aircraft, before the section is going to stall. That's going to allow me to fly at slower speeds, or it's going to give me a greater margin, right, for speeds to fly at before I stall. Of course, usually not all else is equal, so there's maybe some trade-offs here that maybe. So I guess this is what is called CL max, right? That's one thing I want to look at. What's my CL max in general? A higher CL max is going to be better. But I've also got to think about other things. Maybe I've got an airfoil that has a very gradual stall before another one. Let's say that maybe it's a higher CL max, but it's got a very abrupt stall. Even though this green one has a higher CL max, you'll notice that the stall is much less forgiving. There's a very big precipitous drop, so aircraft may drop rapidly. Whereas the black curve is more gradual. I have a little more margin for error, and if I go past my stall speed a bit, I may lose some lift and drop a bit, but it's going to be very gradual. It's going to be more forgiving to me as the pilot or for my autopilot. And so that may be another desirable characteristic I look at. Right? So these are some things we're going to look at. I also want to look at my drag curve. Okay, and just for simplicity here, I'm going to draw versus angle of attack, even though we often will look at it in terms of drag coefficient, or sorry, lift coefficient versus drag coefficient. Of course, a lower drag is better. So if I've got this curve here, and again, if all else was equal and I could just shift it down, I would want the blue one, right? Because it's going to produce lower drag. But the other thing we need to look at is that we want low drag at the angles of attack that we're going to fly at, or in other words, the lift coefficients I'm going to fly at. So if I was to redraw those, let's say I've got one curve that looks like this and another curve that looks like this. Which one do I want is really going to depend on the lift coefficients that I'm flying at. So I kind of drew this a bit too far over, but let's say I'm flying at this lift coefficient here. This is the angle of attack or lift coefficient that I want to fly at, roughly. Then, you know, this drag bucket that's going to put me here is going to be better than, well, I'm way off. Let's redraw the black curve so it's a little more realistic here. Let's say it was over here, right? Then I'm intersecting the black curve here. And even though, and actually let me draw the black curve one more time. Even though this black curve here, maybe it has a lower minimum drag here, but I'm not flying at those lift coefficients. I'm going to be flying maybe kind of in this region of lift coefficients. That this blue one may be more desirable, even though it doesn't have as low absolute drag. It has low drag in the lift coefficients I want to fly at. Now, of course, you don't know your section lift coefficients yet. We haven't gotten to that, but you do know your wing lift coefficient. Your airfoil lift coefficients are going to be a little different. They'll vary through the wing, but for now, on average, your average airfoil lift coefficient is going to be the same as your wing lift coefficient. So I would use that for now, again, as an average. Okay, so those are just a few properties that you're going to want to look at. Well, you probably won't be designing your airfoil in detail. What a good thing you can do is to use some existing airfoils. Now, there are a lot of existing airfoils. You want to pick one that is designed for kind of flow conditions that you're looking for, right? So we're going to be in low Mach. All the airfoils are going to be appropriate for that. But we're also going to be in a low Reynolds number. And not all airfoils are going to be good for that. So one good place to look is if you search online for UIUC airfoil. UIUC is the University of Illinois at Urbana-Champaign. They have a database. And actually, why don't we just go there now? Let's see. Oh, I'm already there, actually. just to show you, I'm going to search UIUC Airfoil. There's this Airfoil data site, and what it is it's kind of a database of a whole bunch of open airfoils from A to Z. And you could search here on this page for low Reynolds number. That will help you find a bunch, but the most of them you'll find are either these Epler airfoils. There's a lot of those. You can see here it says low Reynolds number airfoil. And then the other family of low Reynolds number airfoils that's most common is the Selig. Here's a bunch of them. And if you click on them, what it's going to have is just, these are the coordinates, airfoil coordinates, the geometry. And so you can load this up in, for example, XFlyer 5 or other tools that you're using to analyze these airfoils. Okay, so this will be a good place to find some low Reynolds number airfoils, maybe pick a handful of these to analyze and compare, performance. Does it give you a good seal max? Is it in the low drag in the angles of attack that you want to fly at? Does it have a relatively forgiving stall? And also another consideration you might look at is thickness, right? You want an airfoil that's maybe not too heavy, but also stiff enough. If it's too light, it may be too floppy. If it's a really thick airfoil, it may add a lot of weight. We'll see later that for many aircraft, transport aircraft especially, thicker airfoils are actually lighter, but in this case where most of you will be using a foam wing, that's not going to be the case. A thicker airfoil will be heavier. So you want to make sure that it's a reasonably sized airfoil as well. So anyway, this is just some things to look at. As you go on and maybe learn more about optimization in other classes, we can do some more detailed design for specific things. Let me just show you just for fun here. This is a video from one of my colleagues, a friend of mine who's got a really nice example of an optimization. Yeah, here we go. So in this case, they're doing an optimization for a specific Mach number, and they're going to start with a circle, basically. Basically, it is a circle, and we're going to put in the flow conditions they want. They got a Mach number, and they're trying to minimize drag, I believe, for a given lift coefficient, and it's just going to optimize that shape. There's a lot of parameters here, so it's changing that shape to give to now suppress some of those shock waves. That was fast. Let's do it one more time. Sorry, the bottom's a bit fuzzy, but you can go search this yourself and see it. And these are the kind of tools that you can use to really kind of customize. So in this case, we're not going to customize for our exact flow conditions that we want to fly at, but in this case, a good practice will just be to find some existing airfoils and find one that works reasonably well for you. Okay, we'll see you next time.